Okay, language equivalence. So, all of this is ignorable for this. Recall that two rejexes or two regular expressions are language equivalent if they define the same language, e.g. A, B, or C, and A, B, or AC are language equivalent. So, these two regular expressions both accept the same words. A, B is accepted by both of them. AC is accepted by both of them. If you have something like ACC, this is rejected by both of them. So the set of words that both of these regular expressions accept are equal. Okay, it's not obvious how we can test whether two regular expressions are language equivalent, but we can easily test whether two deterministic finite automaton are language equivalent. So if we have two DFAs, we can check if they're equivalent quite nicely. One thing to note, this does not work for partial DFAs. So we have to, if we have two partial DFAs or you have a partial DFA, just define a held state and any undefined transition should lead to that. But if we have two total DFAs, then fun, we can check if they're language equivalent. So, suggestion, let's build an automaton-like diagram consisting of pairs x, y, where x is a state of the first automaton and y is one of the second. Start at the initial state of each automaton, so starting 1 here, 3 here, and we trace through it. So we say, okay, we're going to start at 1, 3. From 1, 3, where can we get in the first automaton with an A, and where can we get with a B? We can get to 2 in this first automaton, and then from 3, we can get to 4 here. So we can get to 2 or we can get to 4 in each of the corresponding DFAs. These are both accept, so this can be marked by an accept state. And we repeat this for every possible transition. So eventually, this will give us a new DFA, which represents both of these two DFAs. So we had our original DFA and our second DFA, and we traced through both of them simultaneously. We started at 1, 3 in both of them. If we read an A, from 1 in our first one we get to 2, and from 3 in our second one we get to 4. And so we end up with this DFA here. Each pair in here should both be accepting or both be rejecting in order for the two automata to be language equivalent. Because if we think about it, if one of these is rejecting and one of these is accepting, that means if we read in a sequence of characters to get to that state, A will accept it and B will reject it, or vice versa. We want them both to agree on rejecting or both to agree on accepting. And so both of these states have to either be accept states or both have to be reject states. Why would this not work if both are partial? If we had a partial DFA, so say we had, okay, I think if we can think of an example, so say we had something like 1 A sigma equals A B A B, okay, and then we had something like 1 A B A okay, are these language equivalent? Wait, so this accepts I think I need that. A B A oh, I think I need an A going here. Okay, so if we have these two DFAs, I believe they are language equivalent. If anyone can find a counterexample as to why they're not, let me know. But yeah, we can also minimize both of them and see if they're isomorphic, because they both have the no accept states, my bad. Yeah, we can also minimize them both. If they're isomorphic, then that means they're the same. If they have the same shape and structure, we don't care about the state names, then they represent the same language, because there's only one way we can minimize a DFA in terms of the shape we get. Okay, so if we have these two DFAs, let's call this DFA A and let's call this DFA B. So if we read an A from 1 here, so we start at 1, 1. If we read an A, we'd get to 2, 2. So 2 in both of them. If we read a B from 1, 1, here, we've not actually defined anything, so we can't put anything here. That's why we need to define some sort of state, because then we're going to be comparing those two states between the two. I mean, you could just put an X saying we reject it, but in that way, what we're basically doing is we're creating this X state. in order to trace through it. So that's why it wouldn't really work with a partial DFA. We have to have a total DFA, just so that when we trace through both of them, in that pair, they're both defined states that we're comparing. But yeah, if you just want to do it with partial DFAs, you could always just write it like this, for example. But that's the same way as imagining there is some reject state. So either way, it's two total DFAs. The same goes for determinizing, right? So when we're determinizing when we're determinizing an NFA, not quite. So when we're determinizing an NFA, it doesn't matter if some of the things aren't defined. That's where we would introduce, because when we determinize, we're just simultaneously running every possible path. Partial epsilon NFA to partial NFA to NFA to DFA. There's no such thing as a partial NFA, right? It's just an epsilon NFA to an NFA to a partial DFA to a DFA. The DFA is what's partial when we don't have all of the transitions defined for every character.